One. Welcome to Korosi Indonesia podcast. This podcast is a part of Indonesia Association of Materials Protection and Performance, AMPP Indonesia chapter. My name is Richard Bassery. Today, together with my co-host Menas Wibowo, in this podcast, we will talk about pipeline clad and mechanical line pipe clad MLP. Clad and mechanical line pipes, or we can call MLP, is used particularly in the oil and gas industry when production fluids are corrosive. However, it needs to be operated in high pressure and also high temperature. Using clad materials can save 25 to 40% cost compared to the solid CRA pipe or pipeline. So recent manufacturing technology has allowed mechanically CRA line pipe to be inserted into the carbon steel base pipe and seal with the both end use a CRA clad weld. The new technique claim will be reduce the pipe cost up to the 40% lower, and the new technology called MLP, mechanically line pipe. So in today's podcast episode, we will discuss all about cladding pipeline and also mechanically aligned pipe with Mr. Paul Montague. He is the Director and Executive Vice President of Business Development on Product at Cladtek worldwide. As we know together, Cladtek is one of the biggest cladding pipe manufacturing with a big presence in our country, Indonesia, and also with manufacturing facility in one of the provinces in Indonesia, precisely in Batam. Okay, let's welcome Mr. Paul Montague.
Good evening, Richard. Thank you very much for having me on, and thank you for Corrosion Indonesia to invite me and give me the opportunity to meet you and talk to some of your podcast listeners and viewers. It's a pleasure and an honor, and it's nice to meet you and Pak Menas.
Yeah, thank you, Pak Paul. So welcome to Kosi Podcast Indonesia. And would you tell us more about yourself? Of course, I already mentioned a little bit, I think very brief information. I believe our listener want to know more about yourself and maybe your work experience, what's bring you to the business, maybe your education, maybe, and also your hobby in the spare time.
Sure. So I'm quite old now. I'm 57, so I've been in this business for a long time. My family was in the drilling business, and so I went to school like most people, and then I studied a little bit after school, and then I worked in the drilling industry for a while. So I have, I guess, hands-on experience drilling water wells and oil and gas wells from my late teens and early 20s. So I've been involved in the oil and gas and energy services business all of my life in various facets. After working on oil rigs, I then moved and worked for a manufacturing company that built pressure vessels and heat exchangers, also mainly in exotic materials. The company was called Specialized Welding in Australia. So in that role, I was working in their quality department and helping with data books and traceability and those kinds of things. And then I moved into a procurement role, and then eventually I got the idea to start my own business, which was a company trading pipes and fittings. And in fact, that company, PT Mitra, or PT Mitra PFP, or PT Mitra Galperti in Indonesia, was an offshoot of that company, which is from many years ago. And that's where I got more interested in CRA materials, and that was the specialty our business had. And over time we built up businesses from Australia through Singapore, Indonesia, Malaysia, specialising in corrosion-resistant alloy piping packages. Then a little bit later, my cousin and I started another business in Batam called PT Profab, which is now part of NOV, or Profab NOV, that builds modules and skids. And in that business, we were doing some clad vessels by the overlay process. So we had electroslag welding, which is a method of cladding carbon steel shells and heads, and we had hot wire TIG cladding for doing nozzles and vessel penetrations. And through the years of working in those industries, I came across the mechanically lined pipe product that was being produced at that time by Nippon Steel as a product called C2. And that complemented the JSW hot roll bonded. I'll get into the different types of cladding in a minute. And also there was a German company called Butting making mechanically lined pipe. But thinking back to my drilling days, if a steel casing was damaged or had corrosion problems downhole, we had a technique where we put a thin stainless steel liner on an inflatable oil-filled packer, and we used to run it into the damaged area of the casing, and we would use hydraulic pressure or swaging, hydroforming, to form a patch inside the casing or tubing that was corroded, and put a corrosion-resistant alloy patch. So when I saw this product being used for flow lines and things, I thought, well, the technique that we used to repair water wells, if we just turned that on its side, we could make pipes. So that's how Cladtek was born. So we started doing some trials in 99, 2000, and then eventually Cladtek was started in 2003, and we got our first order on the 24th of December 2003. So it was like a Christmas present for us. And the reason we started although the company was founded in Australia and we built some of the equipment that we used to produce our mechanically lined pipe in Australia, the first production site we had was in Batam. And we set up in Batam because Profab was already there, so we already knew we had access to people, we had access to utilities, and we set up there. So we had to get the plant up and running, and we had to produce the first project for a company in Australia called Santos, and the project was called Mutineer Exeter, and we delivered that project in 2004. So that's I guess the summary of how we ended up in the mechanically lined pipe business and to be based in Indonesia. And now the Indonesian operation is still our foundation, production site, and the largest in terms of overall capacity and in diversity of product offering. And that equipment manufacturing function that was originally in Australia has now moved to Indonesia as well. So when we set up in a new location like in Brazil or in Saudi, we build the equipment in Batam and we send it over there, and then people from our team in Batam go and commission it and set up the plant. So that's kind of the story of how we ended up in the MLP business. And how we grew the World Overlay business, which complements MLP quite well, is that when we joined the business, mechanically lined pipe was finished at the end with a thing called a seal weld, and installation contractors didn't really like that, and we came up with the idea of finishing the liner short and overlay welding and machining the end of the pipe. So that enabled very good tolerances, and in case of cutouts and things like that was much easier to deal with. And the line pipe project business is quite lumpy. So having had that overlay capacity, we decided to diversify into general weld overlay and spooling to keep the operation running between line pipe projects. So that's That's the short history of Paul.
Wow, I think very comprehensive. Thank you, Paul.
Thank you. Thank you for the introduction about yourself and on the business. It's very interesting. And actually, following up to that, if you can maybe give, if we take one step back and on the pipe cladding and lining. So maybe some of our listener still need to get about this cladding and lining, and also the various applications of cladding and lining. Maybe can you elaborate on that, on maybe downhole flow lines, risers, or where it can be used?
Sure. Sure, I can do that. So when we use the abbreviation CRA, we're referring to corrosion-resistant alloy. And then when we talk about clad or lined products, we are talking about typically a carbon steel. Sometimes it can be other things like a nickel steel for low temperatures or a chrome moly for high temperatures, but almost exclusively it's just a carbon manganese steel substrate, which is there obviously for its cost performance and mechanical strength. And then a layer of corrosion-resistant alloy is applied to resist the media on the inside. So well fluids in the case of wells, or steam and chlorides and things in the case of a geothermal well, and things like that. So, first and foremost, the initial problem is, okay, I've got an oil and gas discovery and I've got high CO2 or H2S and water and things like that. So the decision is, can I produce this with carbon steel? Because that would be the cheapest option generally. And so there's two selections there. Can it be with carbon steel? Yes or not. So sometimes it's even with chemical injection and things, it's technically impossible. And you have no choice but to go to some sort of corrosion resistant alloy, whether it's solid, clad or lined. And then sometimes it's an economic evaluation. So carbon steel and chemical inhibition and pigging and inspection and all those sorts of things would work technically and might be the cheapest thing to do at the beginning of the project. But then when you consider over the life of the project, the cost of the chemicals, the cost of the inspection, potential downtime, risk of spills, maybe in the case of H2S, if you're in a populated area where a leak could be fatal. All these things come into the evaluation of will I go with a CRA solution. So sometimes it's an economic evaluation, other times it's technically the only solution. So once you've decided that you're going to go with a CRA or a corrosion resistant alloy solution, you've then got a range of choices. Would you use a solid material? So, if it's thin wall, low pressure, you might go with a solid material. Will I use metallurgically clad? So when we talk about clad or lined, or when you look at specifications like DNV, OSF 101 or API 5LD, they talk about clad and lined materials. So when people are referring to clad, they're generally meaning the corrosion resistant layer is metallurgically attached or bonded onto the carbon steel layer. So that can be done by a number of processes. Explosion bonding, which is exactly how it sounds. So a carbon steel substrate, a CRA layer and plastic explosives is put in a remote location. The explosive is set off, and that's enough to bond the CRA layer. So that's called explosion bonding. Hot roll bonding, where they put the two layers together in a steel mill, roll the plates through a steel mill, and through that pressure and temperature of the rolling process, those two become metallurgically attached. And or weld overlay, so either by a hot wire TIG, sub-arc, electroslag, or one of those welding processes, you can apply a corrosion resistant layer to the material. So that's the different ways that you can do metallurgical cladding. And then lining is where the liner is not metallurgically attached. So if I was to cut a ring of the pipe, the liner would stay in because it's held in by like an interference fit or a compression fit, or something like a bearing can be fitted into a housing. That kind of just mechanical interference. But if I was then to slice that pipe longitudinally, that ring, the 2 bits of liner would fall out. They're only held in there by the interference fit between the two. And then at the ends of those pipes, they're overlay welded and machined. So from an installation contractor's point of view, it's attached, but in the body of the pipe, it's just a liner. So what are the pros and cons of the different options? Is obviously a solid CRA gives you corrosion resistance on the inside and the outside, but it's also, can be very, very expensive, particularly if you're in high pressures or high temperatures, because CRA materials generally derate quite quickly with high temperatures. And sometimes, like in a subsea environment, alloys like 316 or 825 aren't resistant to seawater, whereas good old carbon steel with some paint and anodes is resistant in seawater. So there's various considerations as to whether a solid alloy would make sense or not. Mostly for subsea, it doesn't make sense, both on cost and for technical reasons. So then, okay, if you're going to use a clad or a lined, I need to decide, am I going to use clad or lined? So if I'm talking about process piping, where I have to do lots of cutting and joining and rebeveling and instrument connections and things like that, then clad is definitely the better solution. It's a much more user-friendly product for cutting and joining, rebeveling, bending, all those typical sort of fabrication processes. For a flow line, though, where it's going, 10, 20, 5, 10, 20 kilometers with very few, connections and things like that, then mechanically lined pipe, or MLP, offers very good performance, very good cost and performance, balance compared to metallurgically clad. I mean, metallurgically clad will do that job, as will lined, whereas lined, you would not recommend lined for process piping, because it is not, you can cut it and join it if you have to in the field, but it is not very user friendly for cutting and joining. So it's better to use in the full lengths. And then typically on a mechanically lined pipe installation, there will be some metallurgically clad for the plets and plems, end manifolds, bends, and those types of components. So a clad system can be all clad, or maybe a combination of clad and solid materials. So for small bore offtakes and things, quite often there'll be a spec break. So say below 6 inch, they'll go solid. Above 6 inch, everything will be clad. And then in the case of a lined system, you'll always have a combination of lined and clad in that system, and maybe for some instrument connections and things, you may have some solid small bore components. So that's the kind of selection criteria. Why? So then when you're comparing, because you can use clad for both, but it is typically, very roughly twice the price of lined, and typically has poorer end tolerances. So one of the most critical things with a flow line being laid off a barge is end fit up is very critical, and high speed welding, good tolerances. So that is one of the benefits of, mechanically lined pipe is often looked at as the poor cousin of metallurgically clad. But for a flow line, that's not really a fair assessment, because you're not going to cut it and join it and make bends and things out of it. It's just getting fluid from A to B. And if you look at flow line failures around the world for clad or lined has virtually nothing, and the clad ones, and clad has a bigger market share since the dawn of time. I mean, lined now, today, in terms of what's sold, lined has a bigger market share, but since the dawn of time, clad does. But if you look at failures, it's not the pipe itself that failed; it's high-low at the girth welds that create the problems. So for a lined product, the benefit is the good fit up that the machining and overlay process at the ends give you. The considerations you have to think about, though, is things like if you're installing it by reeling, lining will buckle before a metallurgically clad pipe. So in the case of reeling, you need to adjust the liner thickness. It's an engineering problem. It's not black magic. Or you need to pressurize or things like that. And all those things need to go into the evaluation as to whether or not you choose clad or lined. But generally for a flow line, lined is, I would say, the best technical solution and the most cost effective. The other factors that we see coming into play a little bit more now is the ESG component. So one of the things is driving the lower cost of lined is it's using less resources, which is why it's lower cost, and it has a lower CO2 footprint, roughly 40% lower compared to clad. So that is not a big driver on a project, but it gets, I guess, for people that always, oh no, we only use metallurgically clad, now it gets you to the point to have a discussion with them because they're thinking about everything they can do to reduce their CO2 footprint. And the other key advantage that lined has is at the end of life, you can pull it out, cut the ends off, collapse the liner and pull the liner out and scrap it. And metallurgically clad is not recyclable in any normal sense because a carbon steel mill can't melt it because they don't know what they'll get when they melt it. And it's not economic to try and get the liner out. You'd have to cut the pipe up into little rings and machine all the liner out would be the only way. So it's a much more recyclable product. So as well. Now, doing an NPV calculation for an oil and gas project, whether I can recycle it, get some scrap back, or my CO2 footprint's a bit lower, is not really moving the needle. But where now, these are considerations, it is certainly enabling MLP to be considered, a bit more from clients who are perhaps previously resistant. And the other thing is the experience is growing. When we first entered the industry, the biggest installed was 16-inch. Now the biggest installed is 24. We have an order running at the moment for a super major for 32-inch. So, the market is getting more comfortable with bigger sizes as well.
Yeah, maybe so even in my facility also, we have 24 clad. Yeah. So, Papa, can I just got you there? So we still have array of questions.
All right, I'll try and truncate my answers a little bit.
It's okay. I see the spirit there. So I think we want to bits by bits to know about that technology, because I'm sure a lot of our listener maybe those who are not really familiar with this technology. So I think a couple times you mentioned about the weld or joint technology involved in this manufacturing process of even clad materials or the MLP. So can you tell us more about the welding technology used in this MLP or clad pipe manufacturing? And then what is the welding parameters? I think you mentioned briefly about welding speed, but I think it will be more than that to produce sound joint. And also, what is the quality assurance non-destructive test method to determine whether we produce the sound welding or determine the defect?
Sure. So from a fabrication point of view, clad and lined are fabricated, from the girth welding or joining point of view. The process is the same. So in terms of welding processes and parameters and consumables, it's all using the same kind of techniques. So looking at process piping, as we like to say, we and everyone else in the clad or lined pipe business, fabricating clad or lined materials is not difficult, but it is different. And the key difference is at fit up. So a normal pipe fitter will present the two components together, and then typically the one that's smaller will get ground away to get the bore to match up. Obviously, if you do that when you only have 3 millimeters of cladding, you're going to grind off the cladding, and that will give you a potential failure. So the reverse is true. You need to butter the other side. You need to add material to the other side, then grind it. But other than that, it's the same as fabricating a normal CRA. So the weld joint itself is full CRA. So if I've got a a carbon steel clad with, say, 316, then I would do the whole girth well with 309 LMO or something like that. If it's a 625 or 825 clad or lined material, in the case of a line, the end would be overlaid with 625 anyway. In the case of a hot roll bonded, the clad would come all the way to the end, but you would still weld that the root, the hot pass, the fill and cap would all be done with a 625 alloy. And depending, in a workshop environment, it will typically be a TIG process for the root, and then MIG or TIG the whole way out, sub-arc for larger components. On a pipe barge, it will typically be automatic MIG, sometimes with a TIG root, and then automatic MIG fill and cap, but mostly full auto MIG. And some installation contractors like Saipem have developed line-up clamps that go inside the pipe that have a torch on the inside that remelt the root to blend out the root and get rid of high-low and smooth that out. So that's the sort of technologies there. It is also possible to do, if you have access, it's also possible to finish the cladding a little bit short and weld externally using a carbon steel filler metal, and then come back inside and reinstate the cladding. Now that sometimes gets done on spool fabrication on big sizes, heavy wall thicknesses, if you have access, but mostly it's all a full CRA weld. In terms of NDT, typically the acceptance criteria for a clad or lined product is quite stringent, because they're considering at the root that you've only got 3 millimeters of material. Now, there are things you can do with that. The ends can be buttered and be made thicker to have a little bit more margin for error. But if you've only got 3 millimeters and your POD's 1 millimeter, so in your NDT system, your probability of detection, then you allow a little bit of high, say a high-low of 1 millimeter, then you're only left with 1 millimeter of, worst case scenario, 1 millimeter of material. So it will be quite a tight acceptance criteria. So typically, after the root and hot pass, there'll be, on a barge, there'll be intermediate NDT, either digital X-ray or UT, and then for the full weld will be on a pipeline will typically be PAUT or phased array ultrasonics. Sometimes it's X-ray. For process piping, mostly it's ultrasonics or X-ray. Yeah, and in the case of where the ends are buttered with overlay, that would also be examined by DIPEN before it was welded together.
Thank you, Paul. Since we are already in the welding discussion, I think one of the key elements is when you have at the girth weld area, when the liner stops, and you have indeed the weld overlay and also with the backing still. So the transition weld between the liner and start of the weld overlay with the backing, and maybe also that the backing material you can have both in liner as seamless as welded pipe.
Correct. Yes.
And you can also maybe explain a bit to our listeners on how critical is the transition joint. Maybe sometimes it's called triple joints also between the liner and overlay and the backing steel.
Yeah, that's correct. It's called the triple point. So that's where you have liner, overlay, and carbon steel. And in a high fatigue situation, so like in a steel catenary riser or lazy wave riser, which mechanically lined pipe is used in that application, and you have a high fatigue duty or requirement, and you conduct fatigue testing, that is typically the point that the failure will start around that area, and from the carbon steel side through. So and that's because there's obviously a transition, an effective change in thickness there, but that particular area has the geometry of a kind of natural floor, if you like. So you've got an unbonded liner that coming into the triple point. So flaws in that area are extremely critical, and in a high strain service, either lateral buckling or, as I said, lazy wave risers, steel catenary risers, that kind of thing, or a pipe in pipe where it's high temperature and has, again, internal kind of buckling and high strains. That area will see a lot of strain. So it's vital that that area has good metallographic metallurgical techniques, so you don't have characteristics, so you don't have deleterious phases, martensites and things like that from excessive heat input. So heat input is critical, and then so is lack of fusion or pores and those kinds of things at that point. So the normal NDT at that point is digital X-ray, and on bigger size pipes, it's a film type X-ray shot panoramically. So we wrap a film around the outside of the pipe, put the source inside and shoot it. But normally the acceptance criteria in that area is, around anything around 0.5 millimeters. So more or less, if you can see it, it's not acceptable. And so that area is absolutely critical. And that, during the manufacturing process, that is, the main area of focus from an NDT point of view. So the primary method is typically X-ray. On the weld overlay section, there'll be dye penetrant examination to check for any surface breaking flaws, and then UT to check for any interrun kind of lack of fusion in the overlay or any lack of bonding. I mean, typically with overlay, you don't get lack of bonding as such, but if you had scale on the carbon steel that wasn't properly removed, that would present like a lack of bonding. So you detect that with UT, because again, when this pipe gets to the field or to the barge, that area is going to be X-rayed again, UT'd again. So nothing gets the installation contractor more angry than finding something in the pipe manufacturer's overlay weld that causes them to cut out a weld on the barge. So it's really critical that weld is, as I said, from an NDT point of view, if you can see it, you don't want to have it there. So because you don't want to be, they want to be able to do a cutout, rebevel the end, and have absolute surety that area of the weld will be sound. And then when the contractor is doing their NDT, that they're not going to see anything that's in the pipe. They'll know what they're looking at in their weld is in their weld, and they know if they've got a problem they need to cut it, repair that they need to cut out.
Thank you. And for the context, I think, sorry if I missed it before, but what's the length and distance of this triple point from the pipe edge typically?
Yeah, so that depends a little bit on, I mean, it's obviously a cost point. I mean, we do fully weld overlaid pipes, so the overlay can be 12 meters long, in which case there's no liner. So that's the obvious one extreme. Typically, it's around 100 millimeters. The longest that we've done on a normal pipeline is 175 millimeters. And the longest that we've done on pipe in pipe where they have an external swage weld is 450 millimeter clad and machined ends. But typically, most projects will be around 100. If it was an onshore pipeline only doing X-ray and cost was really a driver, you could safely go down to about 50 millimeters, which would enable you to do your NDT, enable you to have one or two cutouts, and still leave 20, 30 millimeters of cladding. So, but most projects, I would say these days, land up around the 100 millimeter mark.
Okay, thank you.
Yeah, before we go to the next question, maybe there is some things that need to to get your answer as well. So what has your company Cladtek done to improve the knowledge around the triple point and also to address challenge in this area? And also I would like to know is there any like a repair rate, or can we repair the triple point that's already defect, or we need to just discard whole pipe and then just create new one?
Right. So we don't discard the whole pipe and create a new one, but we also don't repair triple points. So what we do is we come in and we cut back the liner if we have a defect in the triple point, we'll come and cut back the liner around 10 millimeters and do another weld. So basically you get a new seal weld. Or transition weld and a completely new triple point, and in that pipe the overlay will go from 100 millimeters to 110 millimeters. So typically when clients are specifying or contractors are specifying an overlay length, it's a minimum, not a maximum. They can normally happy to have longer.
More. Yes.
Yeah. Well, Cladtek, as I think I mentioned it in introduction. So before Cladtek entered the market, MLP was finished with a thing called a seal weld, which we now call like the transition weld. But MLP, the liner came right to the end of the pipe, and there was like the liner stack protruded past the end of the pipe about 6 or 7 millimeters, and there was a fillet weld at that point and a bevel put on that fillet weld. And that was cheap, so it was very cost effective, but was very problematic for NDT, for X-ray, because remember I said before when I was talking about the triple point, that area, if you like, is kind of a natural defect because you have the unbonded liner joining the weld. So you have these two lines that look like lacquer fusion, because that's exactly what they are, presented in your X-ray. So that was the idea that we came up with, to overlay the ends. And so that had two benefits. One was to move that problem area away from the contractor's NDT area, so move it away down the pipe, and also to be able to machine it to give good tolerances. And then more importantly, if the contractor got a defect in their weld and they needed to do a cutout, again, with a seal weld it was possible, but it was very messy because on a barge you use cold cutting equipment that cuts from the outside of the pipe. If the liner's not attached, when it hits the liner, it pushes the liner away, and you end up with this kind of ragged mess when you finally part the pipe off. So now you've got the liners all pushed away and messy. So you've got to then machine back the pipe till you get a point where the liner's in good contact. Some contractors had developed clamps to hold the liner in place, and they wouldn't put a new seal weld. Other contractors had techniques to do a manual seal weld. So for all these reasons, the industry standard now is basically what we developed in 2003, which is to overlay weld the ends, because it adds a little bit of cost, but still way less than metallurgically clad. But it kind of gives you the economy of lined pipe with the benefits of clad in terms of NDT interpretation and cutouts and things like that, with the added benefit of improved tolerances because every bore is machined.
Interesting, and thank you for this explanation on how Cladtek has innovated as well to bridge between the conventional clad and the pipe. Can we ask you on the more about the future? And I think the trend is nowadays every big companies, the IOCs, they have this trend to, of course, reach the zero emission, reaches the emission, and many countries to follow the Paris Agreement, reaches global temperature. So in that sense, how do you see the MLP pipe to support companies, operators to reach that, and to maybe to support on these renewables and low CO2 technology?
Sure. So I think I touched on it earlier in the podcast. So MLP has a lower CO2 footprint than metallurgically clad. Compared to solid material, mostly lower as well, and that depends kind of on the thickness of the solid material, but lower, and it has the benefit of recyclability. So in terms of ESG, there is benefits there. So it is helping clients with recyclability and reducing their CO2 footprint, at least of their construction campaign. In terms of where CRA clad or lined materials can help with the energy transition, and I guess the energy transition is really driven by the need to reduce CO2 from the atmosphere, and there's quite a few avenues where clad and lined products are really beneficial for this process. And if we start with oil and gas, traditional oil and gas that's getting produced right now, many operators to this day, in the gas that they're producing, there's quite a lot of CO2 contained within the gas that's coming out of the ground. And that CO2 is stripped out using amine units, and quite often, almost always now, up until recently, now re-injection starting to take place, is vented to atmosphere. And even in a gas recycling project, they're still venting the CO2 to atmosphere and re-injecting the gas. So not great for the environment, but great for the re-injection lines and downhole tubing, because good old carbon steel is fine once you take out the contaminants. So where CRA materials can help with that is, as these companies who want to reduce their CO2 footprint, the easiest place to start to reduce CO2 right now is to capture the CO2 that all these guys are venting and re-inject. And it will be re-injected using CRA materials, and they can inject water and gas and oil and gas in like a WAG injection system, and that has the dual benefit of getting rid of the CO2 out of the atmosphere and keeping the reservoir pressure up as well. And you need CRA materials to do that. So that's something that oil and gas companies can do right now before the energy transition. And CRA, not only Clad products, but CRA products are vital for that that kind of technology. So re-injecting wet CO2 and corrosive mixed gases and waters, and that is a corrosive thing. So CRAs are vital for that. Looking to other things like wind and solar, not much in that for Clad products. A little bit in offshore wind for cladding of cable glands and things like that, but really nothing to speak of. But in geothermal, there really is a lot of opportunities, and as geothermal wells are going deeper and hotter, that's resulting in higher pressures and higher temperatures. So great for geothermal efficiency, and also great for how as your listeners will know, as they're corrosion experts, temperature and pressure and contaminants accelerate the temperature. The detrimental impact of contaminants rises with temperature and pressure. So what we're seeing now is that even like geothermal in Indonesia has mostly been done with carbon steel materials, but we're now starting to see on some of the newer projects, and also where they're re-injecting the condensate now and recycling, and it's picking up oxygen and other things, that clad is starting to being used, and around the wellhead components. And we're seeing in projects in the US, we've recently supplied to a project in the US for geothermal, where we supplied the downhole tubulars lined with 625 and some of the process piping, that which is a very high temperature geothermal resource in the range of 300 degrees and very high CO2 and high chlorides and things like that. So, and geothermal is a really good, renewable or non-CO2 or low CO2 energy source, because it's base load. It's not dependent on wind or sun, so that it's very, very good to go alongside of wind and solar. So that's something where, let's say, clad and line products can help a lot, but also we'll see increasing uses of CRA materials as well.
Okay, thank you. I think very excellent explanation.
Yes.
So I think this is like a more personal to you, but and your company. How do you see Cladtek market in Asia Pacific for the next 5 to 10 years? What is the 3 priorities for your company from now to the 5? Is any plan to go for another region or going to another countries?
Yeah, I mean, that's compared to other cladding companies, that's our goal is to play the local content card and bring technology and training to countries. And you can see, so we originally brought it to Indonesia, and now Indonesia is our center of excellence. And now we use our Indonesian base to transfer our technology to other countries. And over coming 5 years, we'd like to be present in other markets, in the US to service the geothermal, and hopefully we have Saudi in the Middle East. We hope to have another Middle East operation up and running in the next couple of years. I mean, and as a company, the world has made it quite clear that the expectation, or the political expectation, is to transform away from fossil fuels and oil and gas. So, that means over time that we will need to diversify our product offerings, and geothermal is an important part of that. We also supply to mining and metals, so not so much to sort of hard facing and things like that, although that's a potential market for us to look at in the future, where our skill set of weld overlay technology can be used for hard facing. And we also have applications in minerals processing, so like alumina processing and caustic environments in spent liquor and those kinds of things. So there is cladding. The biggest market for us at the moment by far is oil and gas, but I would hope in 5 years that oil and gas is, say, half of our market, and the other half of our market is made up of geothermal, mining, and these other complementary and energy, servicing energy transition. And the other thing that Cladtek and all of the cladding companies have been doing for a while is additive manufacturing. So what we are doing is taking a carbon steel product and additively adding a corrosion resistant layer by weld overlay to the inside. Now, there's a little bit of marketing in all of this stuff. I mean, people say that, to give you an example, people say that skipping meals is bad for you, but intermittent fasting is good for you, which sounds to me like the same thing, but it sounds better if you call it intermittent fasting. Well, if you tell someone you'd like to make them a flange or a gasket out of weld metal, they go, "Oh, I don't like the sound of that." But if you say, "Well, we're going to use an advanced additive manufacturing process called wire arc additive manufacturing to make you a flange," they go, "Oh, that sounds fantastic. Let's do that." And
let's do that.
Let's do that. So, and we've started producing gaskets, nickel alloy gaskets, using that technique, and we think it can be applied to many techniques. And I guess it's not been well accepted in the past because the standards didn't exist, but now API is developing standards. We have an accreditation for gaskets, so the market is coming to additive manufacturing, and as welding processes and simulation, software is getting better to simulate what happens when you put layer upon layer upon layer and those types of things. It is becoming particularly for high value materials like Inconel 625, where you make a big block forging and then start machining away most of it. It makes a lot of sense just to build the component that you need. So additive manufacturing, I guess, is the last string to our bow that we want to diversify away just from adding things to the inside of carbon steel. We think we can use our skills and equipment to build other components.
Interesting market and development there. Pak Richard, I think we come to the last question.
Yeah, last questions.
I know.
Go ahead.
Without you, it's almost an hour actually. It's very interesting. And maybe last question to for our listener also, if they want to know more about you or about Cladtek, and they want to check also what product, what liner materials and product is available, services, whether you have bends and fittings and the sizes, or also whether it's 316 and 65 or 317 or things like that. Can you maybe tell our listeners on where they can check the website or to know more about you and the Cladtek?
Yeah, sure. I mean, they can find us at www.cladtek.com. That's CLADTEK.com. You can find us on LinkedIn, and I think we have a couple of YouTube videos as well. So yeah, most of our product offerings are there, and yeah, you can search under Clad and Lined and find there's there's a solution to get you from the wellhead all the way up to the processing facility, through these kind of products with bends and flanges and all the components and the fabrication. About half of what we produce, we do the fabrication as well. As I say, I think I said before, it's not difficult, but it is different. So if you're doing it all the time, then it's easier. But yeah, you can find us on the internet.
Thank you. And anything you want to say to our listener?
Well, I hope that they found it interesting and not too commercial, not too much of an advertisement. That it was informative and just keep an open mind when looking at these things. Evaluate all the options, and as I said, there's no one product that fits all. There's a place in the market for clad and lined and solid materials and flexible pipes and these new exotic material, bonded composites and things. There's you just have to evaluate the options and select what's best for your application. And if they need any help to make any input data that they need, technical data, commercial data to help make that evaluation, we're always happy to help on that front.
Thank you.
Okay. Yeah, okay. Thank you, Mr. Paul, for your time, and wish you all the best for you and Cladtek for future endeavors. And thank you for listening. If you enjoyed this podcast, please ensure to like, subscribe, and share the podcast through the Spotify link and also YouTube link channel. We hope that you find this podcast are useful and support your professional engineering work. If you have questions or feedback, please let us know. You can contact us through email and the description below in the YouTube channel and Spotify channel. Thank you. Stay safe and healthy, everyone. Let's increase corrosion awareness in Indonesia with Corrosion Indonesia podcast. See you next time in Corrosion Indonesia podcast. Okay, thank you. I will stop recording.